We have been talking about imine formation, which involves a couple of different possibilities. The amine is generally nucleophilic enough to attack first, and then you get protonation of the tetrahedral intermediate, the negatively charged oxygen, and deprotonation of the nitrogen. We're not showing those steps here. They're likely fast. The intermediate happens to be called a carbanolamine. I didn't actually know that till I was working on this. And then you need an acid catalyst to protonate the OH group so that it can be a good enough leaving group for the nitrogen lone pairs to kick it off. You get the Benzeneum Ion, which then loses a proton, restoring the acid and giving you the imine product. And we talked about pH dependence, how there's this trade-off between having enough of the amine form versus the ammonium conjugate base. And of course, that's dependent upon the pKa of the ammonium group. And it's challenging because the more nucleophilic amines, strongly nucleophilic amines generally have pKa's corresponding conjugate acid ammonium pKa's in the range of 6 to 10. So unfortunately, you've got this problem where the stronger the nucleophile you use, the more likely it is to be protonated, the less that's going to be there. And weighed against that, you have to have enough acid catalyst present for the carbanolamine to convert to the imine instead of going backwards. So which of these steps, 1 or 3, is rate determining can really depend on the kind of amine you're using. If you're using a strongly nucleophilic amine, probably step 1 is not rate determining. Probably that's fast. And then it's step 3, acid catalysis. Making sure I'm telling you the right stuff. It's probably step 3 that's rate determining. And if that's true, then we would say that step 3 is rate determining and the reaction's general acid catalyzed. Weakly nucleophilic amines may not be able to, and these would be things with conjugate acids whose pKa's are between 3 and 5. These might be things like arylamines, or here's one I didn't actually know, semicarbazid. Have you ever heard of that before? I really hadn't. It's like a urea, only one of the nitrogens is also attached to another nitrogen. So it's like the hydrazine version of urea. In any case, these are both very weakly nucleophilic, and you might actually need acid catalysis, general acid catalysis for step 1. Sorry about the cruddy penmanship. So strongly nucleophilic amines can attack directly, and then usually it's step 3 that's rate limiting. Weakly nucleophilic amines, it might be step 1. A couple other things to be aware of. Amines show up all the time in biology and metabolism. The fact that we can see is because of the aldehyde 11-cis-retinal that's attached to your rhodopsin protein in your eyes via an imine linkage. There are other related imine variants that you will encounter, and so I thought it'd be useful to talk about them briefly. So this is methoxylamine, or an alkoxyamine. And if you make an imine from this molecule, the resulting product is called an oxime, and it's very stable. So some people have used oxime type linkages in biological contexts because biology doesn't use alkoxyamines, and they react very quickly with aldehydes or ketones. So you can use this as a strategy for connecting two different molecules, or for conjugating one molecule to, say, a protein that happens to have a ketone in it. Let's see, I wonder if my son was playing Among Us. That's fun. There's a specific example, but I can't from the lab of a friend who was a postdoc in the Gelman group at the same time I was there, where he uses an oxime linkage as a replacement for a peptide bond in a protein. You'll also hear about using hydrazine as a nucleophile. So if you add hydrazine to a ketone, this is hydrazine or jet fuel. The corresponding imine compound is called I believe, hydrazone. Not to be confused with a hydrazid. A hydrazid is the amide version of. Anyway. So hydrazones and oximes are quite stable. And then if you want to go really crazy, you could consider making an imine out of this molecule. I think you would then call that a semi-carbazone or something like that. That's really way out there. I've never even seen that kind of compound, so I don't know who would want to make that or why. But you will see hydrazones and oximes, and it's useful to know what they are. All right. I think that's enough about imine formation. Yes, go ahead.
Yes, sorry, just to take us back a little. I think I have the whole thing all confused up. What you said, the strong nucleophile will attack directly.
Yeah.
And that means that, but rather you now said step 3 will be the rate determining step.
Yes, there's multiple things at play here, so that's probably too simplistic because, of course, pH will matter.
Okay.
Right? So, but in general, for strongly nucleophilic amines, forming the carbanolamine is fast. It's elimination to the imine that's slow. And for the weakly nucleophilic amines, you'd actually need the acid catalyst in both of these steps. You'd need to protonate this first before the nucleophile can attack to get the carbanolamine, and then you would need the acid catalyst again to get to the imine. There's just a ton to do, but what the heck. There's some really interesting imine chemistry in biology, and it's related to amino transfer reactions. And this happens to be one of the questions, I think, in the Chapter 10 study guide that Samantha and I were talking about the other day. And I thought it's interesting enough that it'd be useful to talk about. So, but I'm going to get it wrong, so I bet. 1, 2, 3, 4, 5. So I believe this molecule is called alpha ketoglutarate. And it is an intermediate in the citric acid cycle. It's an intermediate in metabolism. So it's a metabolite that's floating around in your cells. And biology can convert this from a ketone into an amino acid. I'm not showing side chain stereochemistry because I'm lazy, but now this becomes glutamate, the conjugate base of glutamic acid, and you can use this in to make proteins. The code for glutamate is E, by the way, in case you care. Now, as you look at these two molecules, the difference is we used to have a ketone here, but now we have an amino group there. And if you think about what had to happen for that to occur, you might think, oh, well, maybe it's reductive amination. You guys have heard of reductive amination before. This is where you take a ketone with acid catalyst and some amine. You make the corresponding imine, and then you reduce it with some reducing agent, and that gives you the amino compound. It's a way of carefully and stepwise alkylating amines. But this is not a reductive amination reaction. Instead, what biology does is it uses another amino acid and a cofactor to trade which molecule has an amino group and which molecule has a ketone, with some really sort of, I don't know any other way to describe it other than it's sort of cute. It's sort of cute chemistry. That's probably not good or right, but the cofactor is pyridoxal phosphate. And here's what I'm going to get wrong. Dang it. So, Samantha, if you've got your notes, maybe you can help me out. There's a phospho group there. There's an aldehyde here, and I think there's a methyl group somewhere. I just don't remember where. I guess we could Google it too.
Oh, I have it. I think it has an OH right next to the carbonyl, the aldehyde group.
Okay, cool. Anything else?
And then a methyl next to the N, right below the OH. Yep.
Okay. So pyridoxal, I guess I could have figured that out from the name. Phosphate. The biochemists love their acronyms, so they'll call this PLP. But what happens here is to get an amino group here, we need another amino acid that we're not using. So, and in this way, biology can transfer around amino groups as it needs to. And let's just say we're using alanine. And I'm not actually sure what amino acid would be used here. We're just doing an example. So maybe we should be as general as possible. We'll just leave that group off. We won't say what it is. We'll put R there. There we go. And I guess one thing I should point out that if you wanted to just transfer a single amino group, you might ask the question, and there was no alkyl group on it, you might ask the question, why can't we just use ammonia and do reductive amination? Certainly, biology has reducing agents. So what's the problem with ammonia? And the answer is it's toxic and it will kill you, right? You don't, if you've ever smelled household ammonia cleaning, it's really sort of repugnant to your nostrils and you don't want to have that around. So this is a safe way of transferring amino groups. And what happens is, first, you get imine formation. And we won't push arrows, but that would involve attack of this nitrogen on this aldehyde to get the carbanolamine, and then elimination of water to get the corresponding imine. So let's draw what that intermediate looks like. Here's the phosphate group. And then here's the imine. Except maybe I don't want to draw it that way. Maybe I want to draw it this way. Okay, so we've condensed this amino group with this aldehyde. Now we have the imine and we lost water. But there's something interesting about this imine intermediate, and that is that the double bond with the nitrogen is conjugated with the aromatic ring, and because that pyridine ring is in its pyridinium form, with a positive charge on the nitrogen, that ring is an electron sink. It's a little bit electron poor, and maybe you can see how we could draw a resonance structure for this intermediate. It might not be a great resonance structure, but hopefully you can see how we could draw a resonance structure in which we move the electrons in this bond over onto the nitrogen. And make a double bond here. And I guess if we did that, we'd have a positive charge on this nitrogen. Like I said, it's probably not the best resonance structure. But what I mean is that now we have a proton on the alpha carbon of the amino acid, and that proton is adjacent to an electron deficient pi system. And it's almost as though that proton is adjacent to a positive charge, and we've seen that happen in the past. We've seen elimination reactions happen when that's the case. And so actually it's very easy for a base, perhaps from the enzyme, to remove that proton. Or we could show the base removing the proton from here. We just need a few more arrows to convert the resonance structures. And when you do that, and this is kind of cool, when you, oh, I left off all the other groups, didn't I? Take a look at the molecule that we've made. And notice the change. It used to be we had the imine between, I don't know, carbon 1 of pyridoxal phosphate. Now the imine is no longer between carbon 1 of the pyridoxal phosphate and the nitrogen. Now the imine's between the alpha carbon. Do you see that subtle change? It's just a proton transfer. Okay, so this is now an imine, and at this stage we can hydrolyze the imine. And what will happen when we hydrolyze that imine is that we're going to liberate not an amino acid, but an alpha keto acid now. It's like we took this nitrogen, we popped it off the amino acid, and it ends up in our pyridoxal phosphate cofactor that is going to look like this. Except we need see, we traded the nitrogen that was on the amino acid, ends up attached to our cofactor. The amino acid that used to have the nitrogen ends up with the ketone. So we've swapped places with functional groups, doing nothing but imine formation and some proton transfers. We're not totally done yet, but the rest of this to make glutamic acid is just going to involve taking this now pyridoxal phosphate bound amine and alpha keto glutarate. And we maybe don't need to draw all the steps at this point, but we're going to make the imine formation, we're going to make the imine again, now with the ketone that's on alpha keto glutarate. All right, so and then with lone pair here, electrons can kick down and we pick up an alpha proton. We protonate on the alpha carbon from some acid, perhaps from the enzyme. Again, that key step changes which side of the nitrogen the imine is on. Okay, and then we can hydrolyze the imine, and that's going to re-release our cofactor that we can start all over again, and it's going to have delivered the amino group to where the ketone was to begin with. So I like this example because it demonstrates how you can use simple imine forming chemistry and proton transfers to do something really kind of crazy, which is swap places between a ketone and a nitrogen, do some functional group interconversion, and actually there's no reduction or oxidation necessary. All right, so that's a long bunch of stuff. Any questions you want to ask about that? So that's how nature transfers amino groups, and if you hear of enzymes that are called aminotransferases, this is probably the kind of thing that they are doing. All right, so I didn't intend to do that, but I thought it was kind of a fun example. I think we're going to skip over acyl transfer reactions because I feel like ester hydrolysis and amide hydrolysis are things you probably already know enough about. So go back and read if you want to know more there, but I don't know that I could tell you anything today that you don't already know on that subject. I want to talk... There was a loud sound. Like a fire balloon or something like that. Was it coming from out there though, or was it over there? Okay. All right. Well. Okay. I'm guessing it's those people that are speaking excitedly and doing something outside. Okay, sorry about that. So I think we'll move on to electrophilic aromatic substitution because there are some interesting things here that you may not have thought about.
I think you need to continue recording.
It is still recording. Yeah, I didn't stop it.
Okay.
Yep. So electrophilic aromatic substitution is where you add an electrophile, and the kind of substitution, it's an addition-elimination reaction because you take an aromatic ring, some arene, and usually the forward reaction is the slow step, and you generate an intermediate that you might have drawn before like this, right? Because we take 2 of the pi electrons from the benzene ring and we attack the electrophile. What that leaves us is a carbon that is now sp3 hybridized, and what's left is sort of a pentadienyl cation, where hopefully you can see that the positive charge would be shared between those 3 carbons. This intermediate is sometimes called a sigma complex. I don't totally know why, but you may hear that. It's sometimes called a benzeneum ion, and it's something that you can observe spectroscopically. And then usually in a second step, a base removes the proton and restores aromaticity. Usually that step is very far downhill because you've got to go uphill to make the sigma complex. So if you use the steady state approximation, it's basically a situation where the sigma complex is the intermediate. And the rate of product formation here is K2 times concentration of base times the intermediate concentration. You can come up with a rate law, and I won't derive it, but you could do it using the steady state approximation that looks like this. You've got K1 and K2 figuring in there. You've got the arene, you've got the electrophile, you've got the base, and then in the denominator you've got K minus 1 plus K2 times B. Now, if that second step is a lot faster than the backwards reaction, then the rate law simplifies, and you end up with K1 times the arene times the electrophile as the rate law, which looks like a simple second order reaction and sort of conceals the presence of that intermediate. In contrast, it might be that these 2 rates are comparable, and in that case you'd see something called partitioning kinetics, where you don't ever see very much of this intermediate stuff either remains as starting material or as product, and then the reaction rate depends on how much base you've got, and then also on the rate of that first step. In addition to the idea of a sigma complex, there's some evidence that there's a step between starting materials and the sigma complex, and that is that there might be loose coordination between the arene and the electrophile. And this should sound a little bit familiar because we learned in one of the early chapters about the cation pi interaction, how you have an electron-rich face of the aromatic ring, and that you can get attraction between that electron-rich face and an electron-poor cation. And so similarly, the idea that maybe an electron-poor electrophile, even if it's not fully positively charged, might be able to sit down on the ring like that. That would be called a pi complex, and then it would go quickly from the pi complex to the sigma complex. It's likely not rate determining, but you could be aware of that. Where this will come up will be if you're trying to probe reaction mechanisms computationally, and you try to say, okay, I'm going to bring these two, you're going to calculate the energies of the electrophile and of benzene, and then you're going to try to bring them together slowly and find whether there's energy minima or whether you're in a transition state. You might hit an energy minimum that looks like this before you go through the transition state to get the sigma complex, because things have to find each other before bonds can break, and so there might be a loose sort of coordination complex. Evidence that the sigma complex is important comes from, you can actually observe this sigma complex in strongly acidic conditions. So if you do a reaction with, say, benzene and a really strong acid, this is hydrofluoric acid in the presence of BF3. So this turns this proton to being super acidic, and there's some equilibrium here between having the proton on the fluorine versus having the proton on the ring. And you can measure that equilibrium constant, and you can compare stabilities of those sigma complexes. So as an example, let's talk about putting things on benzene rings other than hydrogen to see how this affects the rate of protonation of the benzene ring. So if you just have hydrogen on the benzene ring, we'll do all of this in relative terms. The stability of the sigma complex, we'll call that 1, whatever the number is, okay? Then if you put a methyl group on the benzene ring, the stability of the sigma complex, and in this case, higher numbers or greater, is almost 800 times more stable, okay? And we're going to talk about that. That has to do with the fact that alkyl groups are electron donating, right? And if you have more of them, the stability goes up. If, for example, you put 2 methyl groups on and they're at positions 1 and 3, right, where they could donate electron density into the positive charge, 1,3 dimethyl, the rate goes up like crazy. Sigma stability goes up like crazy. And if you have 1,3,5 trimethyl, it goes up even more. The stability goes up even more. So, and this isn't necessarily surprising given what we know about electron versus withdrawing groups. The connection between this and the fact that the sigma complex is an intermediate in aromatic substitution reactions has to do with if you measure the rate of a given electrophilic aromatic substitution reaction, say bromination of the benzene ring. So we'll call this relative bromination rates. Again, for hydrogen, it'll be 1. You introduce a methyl group, it's about 600 times faster. You introduce 1,3-dimethyl, and it's about 500,000 times faster. You introduce 1,3,5-trimethyl, and it's about 200 million times faster. So what I'm saying is the rate of bromination tracks with the stability of the sigma complex, and that should make sense because if you're doing an energy diagram for this reaction, here's the sigma oops, that's not a sigma, that's an alpha. Here's the sigma complex, here's the transition state. Rate will be determined by the energy between here and the transition state, but the transition state resembles the sigma complex by the Hammond postulate. So this is pretty good evidence. You can measure the stability of the sigma complex directly, and relative bromination rates track with stability of the sigma complex. So that's pretty good, solid evidence that the sigma complex is an intermediate in electrophilic aromatic substitution. Now, we're going to put some numbers on electrophilic aromatic substitution regioselectivity. And in some ways, this answered some questions that I had or that I would get sometimes when teaching about electrophilic aromatic substitution reactions in second semester organic chemistry. All right, so as you know, if you have a substituent on a benzene ring, we'll call it R, and then you do a reaction, you have a couple of different possibilities for products. You can get para substitution, you can get meta substitution. Holy Toledo, what am I doing there? Meta substitution, or you can get ortho substitution. Sound familiar? Kind of bored? By the way, if you're ever giving a scientific talk, don't be afraid to tell people things you think they already know. People love to be told things they already know. It makes them feel smart. So, you know, make sure you give a good introduction when you're giving a scientific talk. Okay. Notice that there's only one way statistically to get a para product, whereas there are two ways to get a meta product and two ways to get an ortho product. So if you're very careful, you can monitor the rates of formation of these three options simultaneously and get an idea of which groups promote faster reactions at which positions. All right? And so there's this thing called partial rate factor. So F is the rate factor. The little subscript is going to be for ortho, meta, or para. And then R is the substituent. And this is going to equal the rate of ortho substitution for that substituent, which we'll divide by 2 because there are twice as many ortho protons as there are para, ortho positions as para, and then we're going to divide that by the rate for the same reaction but with benzene instead, and of course benzene has 6 identical positions. Okay? And we could define similar factors for para substitution and meta substitution. And I just want to show you some numbers because I thought this was pretty interesting. All you get in an undergraduate OChem class really is, well, this one is an ortho para director and this one's a meta director. But the waters can get a little bit muddied. So I'm going to list several substituents here, and then I'm going to show you the ortho, meta, and para rate factors, which is going to tell you relative to benzene how fast it is to substitute at a ortho, meta, or para position relative to a substituent that you have. And we'll do this for a couple of different reactions. The first reaction is going to be just nitration, which is one of the reactions we teach undergraduates. If the substituent is CH3, that is toluene, okay? The relative rates are 38.9, 1.3, and then 45.8. Okay, so here's an interesting insight. Notice for toluene, the rate of substitution is faster at all positions than it is for benzene. I didn't know that. This is what we mean when we say the alkyl group, CH3, is an activating group, right? Because all of these F factors are greater than 1, meaning they're faster than just regular benzene. Nevertheless, you can call it an ortho-para director because the rates are so much higher for para and ortho versus meta. So you've got two different things to think of when you're thinking about electrophilic aromatic substitution regioselectivity. Is it activating or deactivating relative to benzene? And then second, regioselectivity, is it faster at ortho and para versus meta? By the way, could you rationalize why it's faster at para than at ortho? I mean, not by a huge amount, but by a little. Sterics, right? Yeah, probably sterics. Depending on what kind of donating group, I guess you could argue electronics as well, because the inductive donors, that effect should go away a little bit the further away you get from the ring. Okay. I'm not going to say anything about the rationale for these ortho, meta, and para directors because I think you should be able to get that on your own. It has to do with groups that can donate electron density adjacent to the positive charge in the sigma complex. And you can review that as needed. Let's look at some of the other groups. The T-butyl group, this is interesting, is similarly faster at all three positions than benzene, but it's clearly way faster at para than it is at ortho, and again, that explanation is probably sterics. Interestingly, you can see that it's kind of messy in terms of what's an ortho versus para director, though, because T-butyl group doesn't favor ortho that much over meta. All right, we would still call this an activating group, and we might conclude that it's more activating than the methyl group, but its selectivity for ortho versus para is different, and probably because of sterics. Now here's an interesting one that always troubles people. Chloro. Let's look at the rates relative to benzene. So this is nitration of chlorobenzene. 0.028 for the ortho position, 0.00098 for the meta position, and 0.103 for the para position. Notice all those numbers are less than 1, which means that chlorobenzene is deactivated relative to benzene. It is less electron rich, okay? But in terms of the rates at each position, it is still faster at ortho and para than it is at meta, right? Why is that? Why is it deactivating, first of all? In electrophilic aromatic substitution, who's the nucleophile? Benzene ring, right? So electron-rich benzene ring should react faster, right? How is chloro making the benzene ring electron-poor or less electron-rich? Go ahead.
It's electron negative.
Yep, electronegativity, simple sort of dipole thing. If you were to compare the electrostatic potential surface for benzene versus chlorobenzene, there would be much less it would be much less negative electrostatic potential on the ring because of the influence of chlorine. Okay, so that's why it's deactivating. Now let's deal with the issue of why it's an ortho para director. Why might it be faster at ortho and para positions than at meta positions? So let me draw you, say, the ortho substituted intermediate versus the meta substituted intermediate. What's the difference there?
Shouldn't it be ortho-para?
Well, I'm showing you ortho and meta because I want you to think about why ortho/para might be better than meta.
Carbocation. This is
Go ahead, Stephanie.
the carbocation.
Right. What about the carbocation?
I think this is tertiary, one is secondary.
You think it's sharing with what?
No,
It's
the
tertiary.
substitution.
Oh, I'm sorry. The substitution is tertiary. Oh, I see. Okay. So the substitution pattern is tertiary. Now, generally when we're thinking about carbocation stability, the explanation we use is hyperconjugation, donating into a positive charge with adjacent sigma bonds. We don't have any sigma bonds on this chlorine, but what do we have?
No, yes.
Lone pairs, right? And in the case of lone pairs adjacent to positive charge, we don't call that hyperconjugation, we call that full-on conjugation or resonance. And if you have the chloro at that position, you can draw a resonance structure that allows the positive charge to delocalize more. Notice both of these have electronegativity problems, right? Both of them have chlorine adjacent to a ring that has a strong electron deficiency. So they're both equally bad in that way, but there is no such resonance structure for the meta. There's no way to delocalize the positive charge any more than it is here. But with the ortho and para substitutions, you can delocalize that positive charge even more. And so that resonance effect in the sigma complex makes it faster to react at the ortho and para positions than the meta position. All right? So people get mixed up on this all the time. They use sort of shorthand to memorize that activators are ortho and para directors, whereas deactivators are meta directors, and then they'll look, oh, chlorine's a meta direct, chlorine's an ortho and para director. That must mean it's an electron donating group. It's not. It can be an electron donating group by resonance, but that effect only matters in high energy intermediates like the sigma complex. If you were going to look at strength of cation pi interactions, they would be weaker for chlorobenzene than they would for regular benzene because of the inductive electron withdrawing effect. Okay, do you get that idea? Okay. So this is why you want to be careful. Some people will, I guess we're almost done, some people will look at relative nitration rates for, say, the OH substituent versus methyl versus toluene versus chloro versus nitro. It's true that it's 1,000 times faster than benzene for the phenol. It's about 25 times faster for the CH3 group. It's slower for the chloro group, and it's basically negligible for the nitro group. And most people, when they think about electron donating versus withdrawing groups, are thinking about electrophilic aromatic substitution reactions. But don't forget the tools you already have. Don't forget the Hammett sigma values for each substituent that tell you in an unrelated system how electron donating versus withdrawing a group is. And it might be useful to compare these sigma values with these nitration rates to get a sense for where they match up and where they don't. Maybe we'll do that next time, but we're basically done with chapter 10. There's one more reaction I want to tell you about called nucleophilic aromatic substitution, but we'll spend almost no time on that. And then with what time we have left, we'll do chapter 11.
Is our final Q